Our third topic is composition of functions. Composition is a very common way to combine functions. If we take two functions, f and g, their composition, which is written f with a circle then g, is another function which takes the input x and outputs f applied to g of x. Here we've written this definition. On the left, where you see f composed with g, you should read this as the name of a new function. When we apply that to x, the output is f of g of x. The output of g is put into f as its input, and the subsequent output of f is the output of the composition. Let's work through a small example. We're given tables for the functions f and g, and asked to compose f with g and g with f. Let's start with g composed with f. This is a natural order to compose the functions in, since you should think of the inside function as happening first. So we're applying f first to x, and then applying g to the result. Starting with input x equals 1, g composed with f of 1 is g of f of 1, which is g of 6, using our table for f. Using our table for g now, we see that g of 6 is 4. Therefore, g composed with f at 1 is 4. Our next input is x equals 2. G composed with f of 2 is g of 4, since f of 2 is 4. G of 4 is 3, so g composed with f of 2 is 3. G composed with f of 3 is g of f of 3, which is g of 5, and that equals 1 from the table for g. Finally, g composed with f of 4 is g of f of 4, which is g of 4 since f of 4 is 4. And g of 4 is 3. Therefore, g composed with f of 4 is 3. So we've written out our table for g composed with f. Notice that the inputs of g composed with f are inputs of f, and the outputs of g composed with f are outputs of g. Now let's compute f composed with g. F of g of 3 equals f of 1, which is 6. F of g of 4 is f of 3, which is 5. F of g of 5 is f of 1, which is 6 again. And f of g of 6 is f of 4, which is 4. Again, the outputs of f composed with g are outputs of f, and the inputs to f composed with g are inputs of g. Now I'd like to be a little more careful about compositions of functions. You can't always take two functions and compose them. For two functions to be composable, the outputs of the inside function must be inputs of the outside function. Here's an example. Let f of x equal minus x squared minus 3. This is a function which always produces negative values. X squared is either 0 or positive for any number x. So minus x squared is 0 or negative. Once we subtract 3 from minus x squared, we get a number that is strictly negative. Now let's look at g, the square root function. We know the domain of the square root function is the set of non-negative reals. It's the set of all numbers that are 0 or positive. So we can't form the composition of g composed with f, since the outputs of f are negative, and g only takes non-negative values as inputs. G and f aren't composable in that order. Here's the formal condition we need to make a composition. If x, y, and z are sets, and f maps from domain x to range y, and g maps from domain y to range z, then we can form the composition of G composed with F because the range of F matches the domain of G. We know that all possible outputs of F are allowed inputs of G. Let's look at problem 12. Problem 12 asks us to form the composition of F with G and then simplify the resulting formula. First, let's check that these functions are composable. F is a polynomial, and the domain of a polynomial is all real numbers, as is its range. G is a line, so that's also a polynomial, and so it also maps from the real numbers to the real numbers. So when we compose these two functions, we'll get a function which maps from the reals to the reals again. This makes sense since the composition is going to turn out to be a polynomial. F composed with G, evaluated at x, is f of g of x. Since g of x is x plus 5, this gives us f of x plus 5. Before we go on, let's pause and think about the geometry of what just happened. We composed f with g to get f of x plus 5. So the resulting function, this composition, is a horizontal translation of the graph of f. We've shifted it to the left by 5 units. You can tell that it's to the left because the sign is positive. The truth is that the transformations that we studied in topic 2 all came from compositions of functions. Specifically, when you compose a linear function on the inside of another function, you get a horizontal stretch and translation. If you compose a linear function on the outside, you get a vertical stretch and translation. Let's finish off with this formula. F of x plus 5 equals 2 times x plus 5 all squared plus x plus 5. We can expand this out to get 2 times, in brackets, x squared plus 10x plus 25. And then we add the x plus 5. Grouping like terms, we simplify this to get 2 times x squared plus 21x plus 55. That's our formula for f composed with g of x. Try composing f and g in the opposite order. If you take g composed with f, you can expand the outside function first, if you like, to get f of x plus 5. Here I'm substituting in f for x in the equation of g. So here you see that composing with the linear function on the outside gives you a vertical translation of f. We shifted f up 5 units. Our next problem looks like the last one, at least superficially. We're given two functions, f and g, and we're asked to compose them. Let's look at the functions we're given and their stated domains and ranges. F is the square root function. Again, its domain is the non-negative integers. We can only take the square root of a number that is 0 or larger. The square root function outputs non-negative numbers, but we can give a larger set than that for its range. Here we've listed the range of the square root function as the real numbers. Our next function, g, is the function taking x to x squared. This is a polynomial, so it's defined for all real inputs. We could have specified its output as all real numbers, but here we're being more pedantic. We know that when we square a number, we get a non-negative number back, so we've stated that the range of g is all real numbers that are greater than or equal to 0. Notice how the domain of f equals the range of g, and the domain of g equals the range of f. We've set these functions up so that they're composable in either order. Let's look at g composed with f first. This map takes an input from f in, so it takes a non-negative real number in, and it produces an output of g, so its output is also a non-negative real. The formula for g composed with f of x equals g of f of x, which is g of the square root of x. And evaluating g at the square root of x gives the square root of x all squared. If you take a positive number, ask for its square root, and then square it, you get the original positive number back. So the square root of x all squared is just x. It's easy to plot this function, but let's be mindful of the domain and range. Now let's compose in the opposite order. F composed with g of x takes a real number in. X may be positive or negative. F composed with g of x equals f of g of x, which is f of x squared. And f of x squared is the square root of x squared. This looks similar to the last equation we had, but we need to be cautious. If we take a positive number, square it, and then ask for its positive square root back, we'll get back the original positive number. So let's plot f composed with g for just positive inputs. Now, what happens if we put a negative value into the square root of x squared? Let's try with negative 2. The square root of negative 2 squared is the square root of 4, which is positive 2. Notice how this flipped the sign of the original value. So f of g of a negative value is negative x. Let's draw this portion of the graph. You may recognize this function as the absolute value of x. That's our formula for f composed with g.